Let's turn on the creepy screen one last time here. Welcome back. We're going to be talking about multivariate longitudinal again, just to do a little bit of review for sort of the big picture concepts. Where we started last time is talking about time varying predictors, or level 1 predictors. And we talked about the different kinds of effects that they might have. At a minimum would be a level 2 effect and a level 1 effect if they have both kinds of variance, which most of the time a time varying predictor will. So we talked about model specification when you are going to take your time varying predictor and manually distinguish its sources of variance via observed predictor variables. So what not to do was this slide here. This is slide 7. What not to do is put in a time varying predictor centered at a constant into the level 1 model and call it good. Do you remember why this is bad? It's smushed, yes. And if you want to sound more proper, pick one of these other words. But conflated, I like conflated the best because that's like the nicer way of saying smushed. The other ones I think can mean other things in different contexts, but the basic idea is that this predictor has two sources of variance at a minimum, between person intercept for mean differences and then within person deviations around those means. When you put it into the model and you only allow it to have one fixed effect, you are assuming without testing that those two types of effects between and within are the same. They will not be the same almost always in longitudinal data because they are on different scales as well as mean different things. So how do we fix it? The way that I prefer in longitudinal models is what's known as person mean centering, or more generally, variable centering. The idea is that at level 1, rather than putting in the original time varying predictor, so XTI, we take that time varying predictor and we subtract person's mean to create a new predictor that I'm calling within person X. That new predictor has only level 1 within person variation, therefore its effect in the model can only be its level 1 within person effect. So a high value on within person X means more X than usual relative to whatever your usual is. What your usual is up here in level 2. Person mean across time, centered such that 0 is a meaningful value. So if you picked the grand mean of that predictor, for instance, a positive value of person mean X would mean that you have more of X on average than other people. So then when we put them both in the model at the same time, this is slide 10, each has its own job to do. Within person X in level 1 has only level 1 within person variation. Therefore, its fixed effect, gamma 1O, can only be the effect of having more X than usual at that occasion, the within person effect. The level 2 effect of person mean X, which has only level 2 between person variance, can only be the effect of having more X on average than other people. So each has its own kind of variance, each has its own effect in the model, each effect explains a distinct source of outcome variance, and all is good. So pictorially, what we've done is this. We have taken the original predictor, and I have two different colors here for use of different kinds of variance. Do you like that? The gradient colors? Yeah, I'm kind of proud of that. I like that. See, and I took the green part and I made it its own box, and the purple part and made it its own box, right? And this is perfectly fine in some situations in which the only kind of between person variance that's lurking in the time varying predictor is in mean differences. But putting it in this type of picture makes it more obvious that we're not treating X and Y the same way. We're allowing the model to distinguish between person variance at level 2 and the intercept from within person variance in the residual at level 1, whereas we're trying to do that ourselves via observed boxes. So let's not do that. Let's let the model do it for both. So that's where we get to the idea of a multivariate model. Let me skip ahead and show you one of those. Actually, well, before I go there, I'm going to stop here and remind you that, as we talked about last time, If your time-varying predictor also has individual differences in change over time, this is slide 21, it has to be done multivariate. So we're treating X and Y in the same way. We're letting the model distinguish their three kinds of variance: between person intercept, between person time slope, between person residual, and then we can look at the relationships among these different sources of variation at each level. So I showed you a model that you can fit in SAS. For example, this is slide 39. So this is how you can trick software that is univariate, such as, what is it, LME4, what do you use, NLME in our NLME, mixed in Stata, mixed in SPSS, mixed in SAS. Those are all univariate packages. You can trick them into doing a multivariate model if you stack your outcomes to be predicted simultaneously into one column. You create new dummy variables that distinguish each outcome, as well as one to be used as an index, and you put them in the model like this. The idea is that everything in the model is eventually, when it breaks down to level 1 here, going to be multiplied by either dVA or dVB. The A terms turn on when dVA is 1, which is those rows of data. The B terms turn on when dVB is 1. So it is two univariate outcomes at once. Everything is separate. Why we do that is so that we can get, in the G matrix, covariances between the intercepts and slopes within variables and across variables, and in the R matrix, correlations or covariances across the residuals at each occasion across different dVs. So I think this is about where we left off. Questions about any of that? Yes?
Do not have the plus though.
Do not have the, yeah, we need a plus here. It got like, I think it got eaten by this text box, if I had to guess. Let me put that in. Thank you. Yes, there. And I'm going to make that black because it doesn't belong to any of the variables in particular. There, let me make the spacing. Thank you. Yes, here's one of the tips when you become an instructor. When you find typos, fix them right away. Clearly, I did not follow that advice. Otherwise, this plus sign would not still be missing after I've given this lecture at least 7 times. Thank you. I got it now, though. I just got to remember to hit save. So it's there. All right. Other questions or things I've messed up? Okay, do you want to see what this looks like in SAS then? Why not? You're here, right? You want to see something. It's a nice day. You could be out on the lawn drinking margaritas, you know. Well, it's like 56 degrees, right? That's a nice day in Iowa. It's all relative. Last weekend, I had a friend visiting me from Arizona, and she's like, I should have brought my down jacket. Yeah, no, I'm in short sleeves. It's fine. I'm used to this. So here is the example that we have. Those of you who are in Jonathan's Bayesian class, do you do Bayes anything?
Not yet. No.
Not yet. So you could come tomorrow because he's going to do these same models in Bayes, and I'm going to show you them in ML today. So one of the TV shows I like to watch is called Special Victims Unit. It's a Law and Order series. Have you heard of this before? Any of you? Yeah. So they come on TV after other like sorts of drama shows about fire and policemen, Chicago Fire, Chicago PD. And one of my favorite things that happens sometimes is they have like one story that goes across 2 or even all 3 shows. Like there was a story that started out with a fire, and that was like the first show, and all the characters from the other show showed up in the first show. And then we found out, no, there was a dead body in the fire, but it was dead before the fire started. It's a murder. And then we get to Chicago PD, and then it's like, oh, we found out the corpse was raped before it was murdered. Oh, we're in Special Victims Unit. And it's like 1 3-hour story, and it was awesome. That's what I'm hoping this week's going to be for you guys, without the murder or rape. Just like we're starting the story today, we're going to finish it tomorrow. It's going to be awesome. Okay, so here's the start of the story. These are fake data that I made up based on real data. These are data that were started in Chapter 7 and finished in Chapter 9. The story is that I have 2 variables measured over time, 7 occasions. Girls that were approximately age 12 at the beginning, measured once a year until they were 18. And I am measuring, their degree of risky behavior by age. So here is a plot of individual trajectories for risky behavior. It starts to grow as they get older. So risky behavior would be all the things you don't want your children doing. Smoking, drinking, unprotected sex, shoplifting, all that kind of stuff, badness. The predictor is the extent to which the mother monitors their child. So thinking that if you keep a closer eye on your kid, maybe they don't do all these bad things. And so here are trajectories for that variable. And because I've measured each over time, I can show the trajectories between the two as well. So in this last plot on the right, the x-axis is time-varying monitoring. The y-axis is time-varying risky behavior. So if you had to try and guess like what the relationships are based on this picture, what does this look like? Kind of looks like a spider web or something, but you can kind of see sort of a general negative tendency, right? So as monitoring increases, risky behavior looks like it's lower? Maybe. But if I wanted to have a hypothesis, does parental monitoring limit risky behavior? Right? That might be a hypothesis, but that's not a specific enough hypothesis in these data. And Ori, this is what I was telling you, like that's not a specific enough question, right? Because there are multiple ways that monitoring can relate to risky behavior. Intercepts, slopes, and residuals. So we'll talk about each of those in turn. Here's the model for my multivariate model. Look, I've got a plus sign. I remembered it this time. So this model has those 2 variables. I had painstakingly built up the best growth model for each outcome in chapter 7 or chapter 9, and then we added some stuff to it in chapter 7. So I have a covariate that's predicting risky behaviors, intercept, and slope, which is parental attitudes at age 12 about smoking and drinking. So basically like permissiveness. Thinking that maybe parents who are more permissive have kids who are less well behaved. It did not predict monitoring in my example, and so it's not used as a predictor of monitoring. So if we look at level 2, there are 1, 2, 3, 4 random effects here. The quadratic effective age for risky behavior does not have a random component. So that's not going to be part of the story because everybody gets the same quadratic. Also note the centering of time. Because everybody started out at approximately 12, age is within person only, but I centered it at the end. So time 0 is age 18. Because I'm thinking that's when most people are going to be the worst behaved, right? So that's the point that I'm focusing on. I could have picked 12, I could have picked any other time, but I'm picking 18. So that's going to be a little bit different than what we've been used to. Okay, so questions on the setup?
I got a question about the plot.
Sure.
The monitoring versus risky behavior.
Mm-hmm.
It looks like it's not like a line. I mean, I just wonder how it's plotted because compared to the other 2 plots,
Mm-hmm.
like when you see the monitoring around like 1,
Mm-hmm.
it's not like a trajectory across monitoring time. So I'm a little confused how to read that plot.
Well, it's ignoring time, and it's just plotting for your monitoring when it was 1, like if this person had a value of 1, they had a value of 15 on risky. They had a value another time, so this is a scale where it's not just integers, it's the mean on a 1 to 5 scale across items. And so the next time they were slightly monitoring more, they had more risky behavior. So it's a trajectory linking these 2 variables, but it's not specific to time.
Okay, so I should not expect it like because in the other 2, although it's kind of messy, but they still have the pattern like from like there's like a trend from left to
Mm-hmm.
right. In the third plot,
There's
it's
no,
just everywhere.
it's everywhere.
Okay.
Yeah, I mean, it kind of looks to me like it's going down, but that is not going to be a sufficient way to characterize this plot. The other ones I can tell you, monitoring across age does not have a fixed slope. It's linear only and it's a slope of 0. But look at what happens to the variance. Remember what I told you, that pattern of variance narrowing or growing? Dead giveaway for what? Remember? Non-constant, right? Non-constant of a particular form. Random linear. This is a random linear pattern. When you have a random linear time slope in your model, that predicts your variance to change quadratically over time. So it'll hit a minimum at some point. Like in this data, it hits a minimum sort of over here, and eventually, because the lines are crossing, it would grow again. Risky is fixed quadratic random linear. So there's more variance at the end. I could have put the mean through here, and I think in chapter 7, I have a picture that has the means, but not overlaid with the trajectories. But the reason that we have separate lines is those are for separate girls. That's how we connected the lines. Okay, other questions? All right, so there's the model. Now how do I do this? Let's focus on the SAS side, because you know how to do that part. M plus is a whole nother animal. So first step, I have to create a new data set in which my 2 time-varying variables, the risky behavior outcome and monitoring that I'm thinking of as a predictor, but I'm going to treat it like an outcome, they have to be in the same column. So I am creating a new data set called risky stack 2, and the first time through, I'm creating a variable that is just an ID variable. Number 1 is going to be risky, number 2 is going to be monitor. I'm creating my 2 dummy codes, DVR and DVM, and then 1 single column for outcome. The first time through, it's going to be filled with the risky behavior column, write a new line of data. The second time through, it's going to be filled with the monitoring column, write a new line of data. So they're going to be interwoven. 1, 2, 1, 2, 1, 2, 1, 2. And do you know why I have these extra spaces in here? Just as an aside. Because I did not define a length for this category, this string variable. So I'm making this just a string because for an ID variable it doesn't have to be numeric. And if you don't define a length, it takes the length as the first entry. So if I stopped with risky, it would truncate monitor at that many characters. So I cheated and just add the extra spaces into my label. So just as an aside, things I've learned the hard way. So now we have this model, which is the same as chapter 9. I probably should make that internally consistent here. Put that there instead. Same thing. I have 3 ID variables on my class statement. I have families, so it's basically because it's the girl's data and the mother's data, I'm calling that family, but you can think of it as person. Occasion, which is level 1, and then DV, which is the index as to which is which for my outcome column. In the model then, outcome, the column that has both, is my DV. And then I have DVR, DVM. Do you remember what those are going to become? Each is a column of 1s, right? Otherwise known as? And that, what did you say?
0.
U?
No, 0.
0. 1s and 0s. But what are these going to represent? Do you remember? In linear model notation, if I had a predictor that's a column of 1s, what is that predictor? Intercept. I got 2 of them, 1 for each. It's a column of 1s when R is what it's predicting. It switches to 0 when it's M. So think of it as a switch. The reason that I can have both at the same time is because I shut off the global intercept here with this no_int command. I shut off the default column of 1s so that I can make my own in a custom way. Then each subsequent fixed effect in the model age squared, and the effective attitudes is specified as explicitly pertaining to one DV or the other. There is no main effective age here. I have the linear effective age for risky, the linear effective age for monitor, the quadratic effective age for risky, the effect of time invariant attitudes for risky, and the effect of time invariant attitudes for risky multiplied by the slope. So attitudes on the risky intercept, attitudes on the risky slope. On the random line, these are my 4 U's. The first 2 correspond to random intercepts. The second 2 correspond to random linear time slopes, or time as age in this case. The magic happens then, the whole reason to do 2 outcomes in the same model, and it can be more than 2, by the way, it just takes longer. Type equals UN. Remember what that stands for? You guys know this one?
Unstructured.
Unstructured, which means everything gets to be what it wants, meaning all possible variances and covariances are being estimated. So I have the variance of each of my random effects as well as its covariance between the intercepts and slopes, and between the slopes. The repeated line looks different than usual in 3 respects. First, we change the subject to be time within family. So this star just means like each observation is the unique combination of time by family. That way I don't need to make a new ID variable that holds that information. What used to be time on the repeated line is now DV, because what this R matrix is pertaining to is the level 1 residual for each DV. I'm switching the type to be UN here also, because I want each outcome to have its own level 1 residual variance, and I want the residuals at the same occasion to be covaried across outcomes. Okay, questions? Then I am making an M+ file. So there's other variables in this file that I had talked about in Chapter 9. We can ignore most of that. And M+ only takes text data. CSV is what I usually prefer to do because CSV opens neatly in Excel when you double click on it. So this is just taking the same example and sending it out. All right, so here's the SAS results on the next page. The full SAS results are in the download folder that I gave with this example called SAS and M+ files. I just put the parts in here that are of interest to us. So we've got the R matrix. Remember what's in R? Vocabulary time. Level 1 or level 2?
Level 1.
Yeah, so these are level 1 residuals. So 8.3 is the residual variance at level 1 for risky behavior. 0.08 is the residual variance for monitoring. Now, why are these numbers so different? Because these variables are on different scales. Risky behavior is a sum and monitoring is a mean. For that reason alone, we should allow them to be different numbers. The off-diagonal holds a covariance. The R core matrix over here translates that covariance into a correlation, and we come up with the correlation of 0.35. So what does that mean? That's our first of 3 relationships we're interested in. So residual at level 1, why are you off your line today, right? It's after controlling for individual growth and predictors thereof. It's the deviation between your actual outcome and what is predicted by your trajectory. That's what we're working with here. What this means is that if risky behavior is higher than the trajectory thought it would be at a given occasion, monitoring is also higher to some extent than the trajectory thought it would be at that same occasion. Those offnesses, if you will, those deviations, residual deviations, are correlated 0.35. So one of 2 things is true, or possibly both. If you monitor your kid more than usual, more than is predicted by your trajectory, they engage in worse behavior at that same time, relatively worse than expected. Now let's go the other way. What if your kid is engaging in relatively worse behavior than is typical for them? What do? Step up your monitoring. Right? I'm not gonna tell you which is which, but to sort these things out, the way that people will phrase these relationships is using time lags. I might have the lag of risky predict, like last time's risky predict this time's monitor, and last time's monitor to predict this time's risky, to try and tease out the sort of which came first kinds of things. As an aside, I don't have to go into this, but there are papers I can send you. Here's a model that in a path model context that people would use to do that kind of thing. You seen this before? Auto-regressive cross-lag thingy, where we have x at time 1 predicts y at time 2, y at time 1 predicts x at time 2 to try and figure out which came first. And note the title of the slide, a model that needs to die. That's my emphasis. There's a lovely paper explaining why, through algebra and simulations, it needs to die, although that's not their title. I got a chance to review that paper, so I had some say in helping to shape it to be extra great, so I'm very happy with the way that it turned out. They did a great job. But can you guess why I hate this model? What did I tell you at the beginning of class about putting the effect of a time-varying predictor in directly? It's the S word. These paths are smushed. They are both between and within at the same time. Logically speaking, the only way that you can have a lagged effect is if it's a within-person effect, because you are the same person the whole time. So this can't be right. By the same reason, longitudinal mediation models where you do the same sort of thing can't be right either. Sorry, Scott Maxwell. This is smushed. So don't do that. The very last model in this example shows you how to do that sort of idea of which came first correctly. So stay tuned for that. So yes, when people are monitoring their children more than is predicted by their trajectory, their risky behavior is also slightly higher than is predicted by their trajectory. So these things do tend to correspond even after controlling for individual differences in change due to adolescence. Okay. G matrix. What's in G? And feel free to use the labels up here to help you out. Yeah, random intercepts and random slopes. Level 2 things, between person things. So this model says that for each variable, people differ from each other in 2 ways. In their intercepts, which is their predicted outcome at age 18, and in the linear age slopes that got them there. So we have, on the diagonal, the random intercept variance for DVR, that's risky, random intercept variance for DVM, random age slope variance for R, random age slope variance for M. Covariances between them, G-core converts them into correlations. And I've highlighted the ones that are between variables, but there's really only 2 that I'm interested in for the sake of this story. Okay, intercept correlation. Yet another way that monitoring and risky behavior can be related. This is between persons, and it's between persons as evaluated at age 18 specifically. Girls who engage in more risky behavior at 18 relative to other girls have parents that are monitoring them less than other girls at 18. That's what you would expect, right? Parental monitoring is supposed to be good for your children, at least to some extent. Too much is a helicopter, too little is neglect. There's a sweet spot somewhere in the middle. But paying attention to what your kids are doing when they're 18 may be a good idea, since 18-year-olds are morons, by and large. No, there's a technical term for it. There's a developmental hypothesis about this, where there's part of your brain that hasn't finished developing, and it's, you know this, right? Like, yeah, it's like the sensation-seeking, risky behavior part is like 3, but you're in an 18-year-old's body with like cognition and you can drive, and so the mismatch is very bad. So, now I'm a developmental psychologist today. See, that's the nice part about being a quantitative person. You can just wear all kinds of hats, right? Yeah, so monitoring is good for you. How about the slopes? These are changes in each of the variables during adolescence. So girls who grow more in risky behavior have moms who have decreased in monitoring. Now I'll say that again. Girls who grew more than other girls in risky behavior have moms who decreased more than other moms in monitoring. Or they increased less, one of the two. And the reason I say that is because on average, risky behavior increases. So I would phrase this as grew more or grew less, because everything is going up. Monitoring, though, is flat on average. So some of the moms decreased their monitoring, some of the moms increased their monitoring. So girls who grew more than other girls in risky behavior had moms who either decreased less or increased more. Less, hang on, I said that backwards. Decreased more, increased less. I knew I should have got some caffeine today. I said it right the first time. You know what I'm saying, right? Negative relationship, that's where I'm going. So on this page then, let's see if I can highlight them all at the same time. No, not at the same time. 0.35 residual relationship, minus 0.46 intercept relationship, minus 0.25 slope relationship. 3 different ways these variables relate to each other. A model that looks like this. Which of those numbers are you going to get with these paths? None of the above. Some smush of all 3 is what you get. So this model allows us to say how these things are related. It does not allow us to do certain other things in terms of examining these relationships. For instance, what if I think that monitoring and risky behavior are more related to each other in parents who are more permissive? That's a moderation hypothesis. I can't test that this way, because the idea of more related to each other is a covariance. There's no way that I can make a linear model on this covariance and say it varies as a function of something else. Now there is, but I can't do it in mixed. That is a heterogeneous variance model, a location scale model. And those are a pain in the ass to estimate and almost always require Bayes, particularly if you have random slopes. That's where they start to blow up. The other thing I can't do is ask for moderators of this relationship with the residuals. So I can't have, this is a single covariance, which means it's basically a fixed effect. We're assuming that these 2 residuals are related the same way in all girls. We're assuming they're related the same way at all ages. There's nothing I can do to change that in this format. So this is where these undirected kinds of multivariate models are less flexible. I can only do so much. To ask those kinds of questions, I have to go to a different framework. A framework that allows me to specify predictors and outcomes using multivariate models, and that's the only way that I know how to do that is using M+. There are other software packages. I think there's one in Stata. I don't remember what it's called. R has one. There's a package that Paris Meta wrote. It's like XXM, I think. It's supposed to be able to do these kinds of models that I'm going to show you in M+. I have never played with it, so I can't speak for it good or bad. I just know he wrote it, and he has some papers on it, some of which I actually reviewed. It's a very small world out there. Find that out. So, I asked last time, you guys have seen M+ before? Have you seen M+?
No.
No? Okay. Well, it's fun. It's super. I've had to teach workshops like where I start with people who've never seen multi-level before, and I have to do it this way, and it is the most painful experience. So if this doesn't make sense, you're in good company, because this is just a kludgy as hell way of doing all of this. It's a system that it makes perfect sense once you understand the system, but when you're learning it, you're like, what? But it does illustrate why understanding the equations of the models that you're fitting are helpful, because their setup matches the equations. So M+ is a package that you can pretty much do anything in. Structural equation models, multi-level models. Technically, they call this what we're doing here multi-level structural equation modeling, even though there's no measurement model to what we're doing. And any other combination of generalized models, they have link functions, you can do anything. So when I teach a course on measurement and structural equation models, I use M+, because it's the only thing that I know of that does everything. Levon only does certain things in terms of link functions. This will do everything. So for better or worse, I'm stuck with it at the moment. So in M+, the things that are in blue here, and yes, I've color-coded everything so that it looks like it would when you're running the package. Those are M+ commands. There are very few of them. Things that are in capital letters are also M+ commands. Anything that I've put in is either title case or lowercase are things that you would change, names of variables, it's things like that. So M+ requires a data file. Let me get to this, open up chapter 9 here. I gave you the data file. That is a comma separated values file, text, or a DAT file is the other extension that it allows. And I'm opening this to show you something very, very important. Are you going to guess where I'm going with this? Number one thing people screw up when they try to run M+. Number one with a bullet, as they say. What's on the first line here? Data. No names. What happens if you have your names at the top? It yells at you with an error message that is like it's not a helpful error message. Now also, this means that the onus is on you to make sure that you tell it the names of these variables in the order in which they occur. That's the second thing people screw up all the time. So just making sure your data are read in correctly should always be the first step when you're fitting these models. So the names in this here, the file that I'm using, this chapter 9 file, it looks like I took, yeah, this is the one that's in the book. I truncated it down for the purpose of this assignment. So those are the names of those columns. Note that in addition to, note that character limitations, each of these can only be 8 characters or less. Suck.
I think I made that mistake once, and I only have more than 8 characters, but the first I think 8 they're the same, and so M+ still recognize it, but I always have the multi-collinearity issues in the model, and I couldn't figure out why, and try to do all different kinds of diagnostic ways to figure out the multi-collinearity, but later you figured out that because M+ recognize those 2 variables as the same.
Yep. So what she's saying is like occasion here is 8 letters. If you had occasion 1 as one variable and occasion 2, it's going to cut off the numbers that separate them, and it's going to think everywhere that's just occasion. And bad things happen, right? And
It's still working.
it still ran, but it's like, so yes. So the other thing I want to point out is that age squared is a variable here that you have to make ahead of time. It requires you to have interactions between observed variables specified as an observed variable. So it's the same as in like a regression package where you have to make it ahead of time. So I did that. Use variable. This is also very important. By default, it puts every single variable in your data set in the model somewhere, unless you tell it otherwise. So if I forgot this statement, person ID would be a predictor variable in my model. That's not helpful. You have to tell it how your missing data are identified. It allows blanks and dots, but I am superstitious and I've had bad things happen when I did that, so I always fill them in with actual values. There are options that are specific to MLM. These are analogous to what you say in SAS in terms of the subject statements here. Cluster is your level 2 ID variable. You then have to define any variables that are only level 2, such as attitudes here. You also have to define on the within statement here any variables that are only level 1, so that it knows it can only go into the level 2 model or the level 1 model. The type of model we are running is a 2-level model, and random means I'm allowing random slopes in addition to random intercepts. Estimator is maximum likelihood. So note over here in SAS, ML is what we use for this model because REML doesn't exist in the world of multi-level structural equation models. So I ran everything in ML to be consistent. Now, the fun part. Have you guys seen the between within syntax before? You've seen it? Do you understand it? No, thank you for being honest. See, you're in good company. Having seen it before doesn't really help you. But it wants you to write your model in the same way that we write the model in the equations, where we have a level 1 model that has placeholders in it. The betas are the placeholders, and each of those placeholders then gets defined by its own level 2 model. That's what it's trying to do here. It calls these betas latent variables. And it wants you to name them. So, in M+, as you might have guessed, comments in the green text here are started with exclamation points. So I have tried to the best of my ability to tell you what every single line is doing for you. So the within model is the level 1 model. In general, when you list a variable by itself, what you are referring to is a variance of some kind. What kind of variance it is context driven. So, in the within model, I know this is my level 1 model. I am asking it to estimate level 1 residual variances because I'm in the within model. And because I know that these things are going to each be predicted by age, what I'm asking for are residual variances in the sense that these are leftover residual variances. In parentheses are labels. I am labeling some of these parameters so that I can have it do math to them down below in this model constraint section here, which works like estimate statements. So I have labeled this R resvar and M resvar. Next comes these 3 things. These are placeholder definitions, where the name on the left is what you create, and these are functionally betas. So our slope is beta 1 for risky. Our quad is beta 2 for risky. I could have named them that, but I prefer to name them things that I will recognize later as to what they mean. M slope, what's that one? Can you guess? Yeah, beta 1 for monitor. So in these, now that we've named the betas, we have to define what the relationship is that the beta is for. And this syntax, when you see on, means a regression. It's y on x. So age is the predictor, risky is the outcome. And it seems backwards to me because I never phrase it that way. I always phrase it like age predicts risky. It works if you think about this on as being the same thing as an equal sign. So if you write an equation, you always start with y equals the x's. It follows the same system here. So that helps me keep track of which way the ons go. So this is the linear slope for risky, the quadratic age slope for risky, the linear slope for age. And then one last thing here, with indicates covariances. So I am allowing the E residuals for risky at the same occasion to covary with the E residuals for monitoring. That corresponds to the idea of an unstructured R matrix over here in SAS land. So the first line under within is asking for residual variances for risky and monitoring. That's the diagonal of R. The covariance between them then is the off diagonal of R that is added when you switch to type equals UN for your R matrix on the repeated line. Okay. With me so far? Any of that you want to hear again?
So what is the vertical like?
It's a definition.
So if you don't have that part, the M plus will just have use the default name for the slope, like the R slope.
If you don't have that, right? If you just do that, then it will fit a fixed effect that corresponds to this, but you will not have an option to also add a random effect for it, nor can you add any cross-level interactions.
So that is just regular regression.
That is just regular regression. So if all I had was, like for instance, I could do that, let me back off here. I could have done that for this one, age squared, because I only have a fixed quadratic age effect, I don't have a random. But to keep everything looking the same, I didn't do that, but I could have. Good question. Okay. Other questions? Okay, now we're in between. Same rule as before in terms of when you list a variable. Do you want me to make this bigger, Kofung? Okay. Is that better? Okay. When you list a variable, you're referring to a variance of some kind. So because it is in between, writing this down means give me a between variance. It's an intercept specifically. And because these two variables are actually just, because risky is going to be predicted by attitudes, this is actually a leftover intercept variance, whereas monitoring is the original intercept variance. The difference is corresponding to the idea that the monitor intercept here, this U represents all the variance there is to be had, whereas the intercept for risky is what's left after controlling for attitudes. So just by listing those two words, based on the rest of the code, M+ understands whether it's estimating a leftover variance or an original variance. They show up in different places in the output, just to mess with you. Okay, I have labeled these, R intvar, M intvar. Same idea here for R slope, M slope. Those correspond to the placeholders I defined up here. The placeholders, the beta placeholders in the level 1 model in the within, when I list them down here, I am referring to their variances. So what I'm asking it to estimate is a linear age slope variance for risky as well as a linear age slope variance for monitoring. because I don't want a random variance for the quadratic effective age on risky, I shut that off with @0. Default is that everything is estimated. You have to shut it off if you don't want it. Last but not least, brackets. So the makers of M+ have something in their model syntax that goes with every single special character above the numbers on your keyboard. In the latest version of M+ 8.1, I think, they finally got them all. There was only one they hadn't used, and they used it for something, so they are out. They're gonna have to switch to wingdings after this in terms of like model specification. But bracket was one of the first ones. Things in brackets are some kind of mean or intercept for that variable. Now what's the difference? Think back to empty model. If you have an empty model with no predictors, the intercept becomes the mean, right? If you add predictors, it's a conditional mean. It's the mean when the predictors are 0. So for variables that are not being predicted, when you refer to that variable in brackets, you're referring to its mean. So in this case, I'm referring to the fixed intercept for monitoring, which is going to be the expected value of monitoring at age 18. So it's an intercept. Likewise, this is the fixed intercept for risky, which is the expected risky behavior at age 18 according to the model. So they're both intercepts. Also in brackets, R quad, R slope, M slope. Those are the fixed slopes that correspond to each of those betas. So the fixed quadratic age slope is R quad. The fixed linear age slope is R slope. The fixed linear slope for age for monitoring is M slope.
I got a question. So
Yeah.
you mentioned that in order to have the random effects, we need to list the fixed effects first, right?
It's estimated by default. I am writing everything out that's going to show up on our
Yeah,
output.
I just wonder if we omit the bracket for the random slope, is the M+ still recognizing it? Or
If I don't
it
write
has
these
arrows?
things, it will give them to me anyway. The default in these models is to make everything random and have a fixed effect for it.
Okay.
I'm just showing you, to me, it's helpful when there is a line of syntax that corresponds to every row of output, because I don't want to memorize their default system, because it can change between versions. So when I refer to the things in brackets, these are the fixed effects that correspond to those betas. The things then without the brackets are the U variances at the end of that beta. We're almost there. Risky and R slope on @4. So I have two outcomes in this sentence. This is a shorthand way of saying both of these things are predicted by @4. So this is the effect of parent attitudes at level 2 on the risky intercept and on the risky linear H slope. That's what I'm asking for. And then last but not least, I have all possible 6 covariances between risky and monitoring intercepts and slopes, and I have labeled each one as to what it is. And because M+ does not give you standardized results for multi-level models, I tricked it. Model constraint allows you to make new parameters that are linear combinations of estimated parameters. So it works just like estimate, what we've been using for simple slopes and predicted values, except that it also extends to variances. So I am literally computing the correlation that goes with each of these covariances myself, where I'm defining the new term that I'm computing, giving it a name, and then telling it how to make it, where these words in here correspond to the labels that I used up above. So whatever this covariance is at level 1 between risky and monitoring, that number is what it's going to fill in for ResCov when it sees it down here. Likewise, whatever estimate for the residual variance we get for risky and monitoring, each of those is going to get filled in here. Okay, how are we doing? All right, output time. All of these numbers exactly match those of SAS because this is the same model that we just looked at, the undirected model, where all of the relationships between risky and monitoring are specified via covariances. So risky with monitoring in the within, that's my level 1 R matrix covariance, 0.2 something or another. That's right over here. Likewise, the residual variances on the within level correspond to the level 1 E residual variances that show up on the diagonal of the R matrix here. The between level, it does not order your output in the order in which you asked for it. It has its own internal order that, as near as I can tell, you cannot change, and it's very frustrating. But it decided to give me the fixed effects of attitudes on the risky slope and the risky intercept first, slope then intercept. Here's the covariance between the risky intercept and slope that would be in the G matrix. Next are the slope covariances for monitoring and risky with the monitoring intercept, and then the slope covariance and all the other covariances, etc. If you match those, you would find them over here in the G matrix. Down here is means. This is where we're running into job security, folks. If you can understand this stuff, someone will pay you. Means versus intercepts. Same idea, different words used for things that are predicted versus things that aren't. So let's start with intercept. This one is the obvious one, risky. That's my fixed intercept. It's under intercept, right? Now what the hell is a risky slope intercept? How can a slope have an intercept? We talked about this briefly, but I will remind you how. Go back to the equation. This equation, right? If you think about the intercept of this equation, the jumping off point, that thing, that's my fixed slope for monitor. And so this is the fixed slope for monitor. This is the fixed slope. So this thing right here for risky, that is the intercept that it's talking about because it's the first term. And it's called an intercept because there's something that comes after it. So this is the intercept specifically for parents who have attitudes of 4. Whereas down here, the slope for monitoring is unconditional. So it's not going to be called an intercept in M+ parlance. Instead, it's going to be called a mean. It makes sense when you work really hard to figure it out, but it's annoying. Likewise, because we only have a fixed effect of quadratic age on risky behavior that is not predicted by anything, the mean of R quad is the fixed age, quadratic age effect. And it does not have a variance associated with it because we shut it off. So you will see this happen anytime you have a parameter that is fixed to a known value and it's not being estimated. the estimate is 0, the standard error is 0, because that's what we told it to be, and then 9999. That's not a number. That's M plus for because guess what? 0 divided by 0, not a thing. So it just prints 999 to go. It's not a number. And then finally, residual variances. In the between model. That violates our language in this class. What does it mean? It means residual in the sense of left over, unexplained. So this is the rest of the random intercept variance in risky and the rest of the random linear age slope variance in risky. And here are the correlations that I computed. They exactly match those of R core and G core. Okay, how are we doing? Crazy, huh? So the mutanes sleep on a bed of money every night. This package costs $1,000 for you to get a license for it, and you have to pay $200 a year to keep the license active. And they also hold workshops very frequently. I went to one in Virginia as a postdoc, and there were probably 200 people in the room who had each paid $200 a day to attend this workshop. You do the math. They sleep on a bed of money every night, I'm quite certain. Forget the down comforter. This is cash. Their mattress is stuffed with cash. It's much crunchier. So, now why would I put you through all of this here? Well, to be able to take the idea that monitor is supposed to be a predictor and make that explicit. I need M plus to do that. Or Bayes, but that's tomorrow. You can do it in Bayes and M plus, but this is a multi-level SEM. So I want to point out the differences relative to what we're doing before. Rather than writing the equation as everything is predicting one Y and I'm using dummy codes to turn things on and off, because each of these can be in its own model in this software, I can make the equation look like it. So I've got my level 1 model for monitoring, same as before. My level 1 model for risky has monitor in it. So beta 3 is a new placeholder that is the level 1 within-person relationship between monitoring and risky behavior. Similarly, monitor intercept, monitor age is exactly as before, but now I am introducing in the risky lines the idea that I want the monitoring slope and intercept to predict those things. So the betas themselves show up as predictors. The intercept and the slope for monitoring each predict the intercept and the slope for risky behavior. Conceptually, that goes with a picture. Let me find it. Like this. One variance component is predicting another. That's what we're doing here. The code looks remarkably similar, and since we're about out of time, I will point out the places where it differs. Here's my level 1 relationship. It used to be a covariance. Now I'm treating it the same way as the others, where beta 3 is within-person res, so I'm saying that's my within-person residual relationship, and it is defined as a regression of risky on monitoring. Likewise, rather than have with statements between the random effects, I've switched all of those to ons. It's that easy. It's that easy, ... not quite. So I made up these data. I know what the right answer should be. And this number looks wrong. This is the regression of the monitoring slope on the risky intercept. Actually, I think I did the wrong one. I want this one. Yeah, not that one. Hang on. Not that one. This one. That one. And that one. So these are in units of x per unit of y, which is why the numbers are so big. But when I created standardized versions of them, they were wrong. And so this is me sitting at my computer circa 2013, all right? I made these data up. I know what the answer should be, and it was wrong. Fast forward like 3 days of me like chewing on my fingers and like staring at this. These are contextual effects. Remember that term from last time? The other kind of level 2 effect? Because when we put the model together, we have the original version of monitoring as my level 1 predictor. So it hasn't been partitioned for its level 2 variance. So all of the level 2 terms that are consistent with that, int to int and slope to slope, become contextual effects. And I had to then use estimate statements, new parameters, to create the between person versions of those that it should be. And that's why they initially didn't match. So this is the trick to these sorts of models, is trying to figure out in your level 2 model, based on your level 1 model, whether you're going to get between effects out or contextual effects. I can't tell you how many times people have screwed this up unknowingly. I actually wrote a paper about this problem that should be coming out sometime later this year. I'd be happy to share it with you, where it was a tutorial on trying to figure all of this out, because there's no rhyme or reason to it. It turns out that the relationships of intercept to intercept and slope to slope are contextual. But intercept of monitoring to slope of risky is not contextual, it's between. And the same is true of monitoring slope to risky intercept, that's between instead. So your level 2 model is a mixture of different kinds of level 2 effects. And I only figured this out because I made the data up. Like, I never would have known this otherwise. And in the most recent versions of M+, they have expanded their offerings in Bayes, and they've switched it. So you'll hear about this tomorrow. I think Jonathan's got it working, where instead of putting monitoring in here, they've come up with a way to put just the E residual for monitoring instead, which is analogous to person mean centering, which then gives you totally between results. And they wrote a paper, a tutorial on why Bayes is so much better. And they did the same model in ML and the same model in Bayes, and they claimed in the paper that the ML version was biased and wrong. It wasn't. It was contextual effects instead of between. And they were spot on once you controlled for the difference. And that paper made me so mad that I had to write my own paper, and it did. So I'll be happy to share that with you if you'd like. But no, Bayes does not make this better. And in M+, if I took this code right here and I ran it in maximum likelihood, which is what I did, I would get a mixture of contextual and between level 2 effects as shown here. If I took this literal same set of code and I swapped out estimator equals Bayes, everything at level 2 becomes between instead. So starting in M+ 8.1, literally the same code gives you 2 different sets of results depending on whether you're in ML or Bayes. So tread carefully in estimating these models in practice. I would recommend estimating them on a known data set to figure out how your software is working. And the same is true if you use R or any other thing that's not M+. You have to be able to predict what's contextual and what's between. It's super tricky. Okay. Did I blow your minds? Your mind's blown? Oh, and by the way, how many of you have taken SEM, structural equation modeling? Most of you? What we just did is this. There's a picture. Same damn thing. Code looks very different, but this is a single level structural equation model that does the exact same thing that we just did. So you can estimate these multivariate longitudinal models as multi-level SEM or a single level SEM. The difference is that in the latter, random slopes for the relationships between the residuals are not always possible to estimate. Depends on your software. So, ta-da! And then last but not least, the very last model in here shows you how to do the lag relationships properly because they're specified in addition to the intercepts and slopes that keep them unsmushed. So, there's an example of how to do those sorts of which came first questions. So, the end. Questions? Did I overwhelm you? Yeah, that's okay. That's okay. This is why I saved this for last, right? This is job security land. But yes, if you're interested, I'd be happy to send you more papers about this. Since no one wants to talk, I'll talk. I just want to say thank you to you guys. And those of you who keep showing up, even though you don't have to, this whole half of the room here who's not getting credit, you're bad, right? Especially you, Ori. You did all the homeworks, and you're not getting credit. I don't know what the hell that's about, but whatever. I just want to say thank you for showing up. Thank you for doing your work. Thank you for being a great class. I had a lot of fun. I hope this is useful. I hope the materials you can take with you and look back on when you need to review these things, because I don't expect you to know everything you need to know. I don't expect you to remember, but I want you to hopefully have something to come back to. And like I said, you've earned the right to email me in the future if you have questions, so long as you do the same courtesy for those who then email you. If you haven't already done so, make sure you fill out the evaluations for the class through Iowa, through Icon, as well as the one from Qualtrics. You get an extra credit point if you fill it out. That's how much I want your feedback. So, homework 8 is due at the end of finals week. Let me know if you run into problems with that. It should be relatively straightforward, but let me know otherwise. I guess that's it. Kind of anticlimactic. Can we all clap it out? Can we clap it out for everyone? Yeah, we do that at my house at Christmas. Like after everyone's opened their gifts, my brother's like, clap it out, everybody. So, thank you. Have fun. Enjoy your weekend. Enjoy your finals.
Thank you.
Thank you.